x of t a naught cos 2 pi f naught t is 2 pi f naught a naught. Okay. So for no slope overload distortion, what is the condition which we have seen already? The condition is delta of by ts must be greater than or equal to 2 pi f naught a naught. This is maximum slope. Okay, magnitude of maximum slope. Okay, 2 pi f naught a naught, right? And what is required for no slope overload distortion? This amplitude a naught must be less than or equal to delta divided by 2 pi f naught into ts. That is, I take this 2 pi f naught onto the left hand side, then del a naught must be less than or equal to delta by 2 pi f naught into ts. Now, if the sinusoidal signal has an amplitude a naught, what is the average signal power? P max is a square by 2, right? A square by 2. So we can say, if we say this a naught is having, I mean, if the signal is having the maximum power, that is a square by 2, which can be equated to, right? A square is nothing but, I just take a square of this here, right? If I square here, right? If I square here, I'll get delta square, right? Delta square by 4 pi square f naught square ts. This is nothing but a square, and if I divide it by 2, I'll get delta square divided by 8 pi square f naught square into ts square. Okay, so this is the right expression for the signal power. The maximum signal power can be delta square by 8 pi square f naught square ts square for no slope overload distortion. Okay, right? Now, with the no slope overload distortion and the maximum quantization error is plus or minus delta, right? The step size will be, what will be the step size? Delta. Step size will be delta. So step size, we know, we have seen already, this delta equal to 2 times small delta, right? So therefore we can say this delta is nothing but capital delta by 2, right? And we also know that variance of the quantization noise, delta, I mean, sigma q square, is nothing but delta square by 12. So this is with respect to uniform quantizer, right? Delta square, capital delta square by 12, uniform quantizer. Now if we consider it to be a delta modulator is also having two steps, right? Two levels, right? So we can consider it to be a uniform one, right? So we can say delta square by 12 is the variance of the quantization error, and we know this delta square, or capital delta, is nothing but 2 times small delta, or I can say delta, small delta is equal to delta by capital delta by 2. And if it is substituted here for delta, so I can have 2 times small delta square by 12, right, resulting variance of the quantizer of delta modulation. So variance of delta modulation quantizer. Okay, right, right, where sigma q square is a variance of a quantization error of a delta modulation system. Now the average power of the quantization noise is uniformly distributed in frequency interval, right? So average power is uniformly distributed in frequency interval, that is from -1 by ts to +1 by ts. The reason is signal is sampled every ts second, sampling rate is 1 by ts, right? So we can say the average power is distributed uniformly in this range only, right? So now if I take the noise, I mean the quantization noise power spectral density, right, it is something like this, right? And if I say noise power, it is from -1 by ts to +1 by ts. So you can define the average noise quantization noise power is this. Average quantization noise power is this. Now, from this noise power, if I have to get back to the power spectral density, what I have to do? If I have to get back to the power spectral density of the quantization error, power spectral density of the quantization error can be, right, delta cube, so delta square by 3 divided by 2 by s, 2 by ts. Why I have to do this? So the noise the quantization noise power spectral density is, right, something like this, right? Quantization noise power is defined for a band of -1/ts to +1/ts, right? It's a noise power because the signal is sampled every ts second. So we can say in the band or in the frequency interval -1/ts to +1/ts, this defines the area under this noise power spectral density from -1/ts to +1/ts is nothing but the average noise power or the quantization noise power, right? Now if I want to find the quantization error, the power spectral density of a quantization error which is having the wider bandwidth, compared to the signal bandwidth itself, so we can say that by dividing the average noise power, quantization noise power, by 2 by ts, right? So this over totally 2 by ts, right? So this, if I have to find the average power, right, I have to multiply the noise power spectral density by 2 by ts. I'll get the average power. Okay, I'll get the average power. Now if I want to get back to the average, the noise power spectral density, what I have to do, I have to divide average noise power by 2 by ts. This will give me delta square multiplied by ts by 6. Okay, delta square multiplied by ts by 6. So this is nothing but the power spectral density of quantization error. Okay, power spectral density. We have obtained the power spectral density of a quantization error from the average power of the quantization error. Okay, or it is obtained by dividing average power by 2 pi ts. Okay, now if the power, so if the at the receiver, if low pass filter is used, okay, whose bandwidth is say w hertz, right? Bandwidth is w hertz. Say low pass filter has a bandwidth w hertz. Say I have a low pass filter whose bandwidth is w hertz, right? Whose spectrum I can say is this, an ideal low pass filter, maybe it has a bandwidth w hertz. Okay, then the average quantization noise power, now I have got average quantization power spectral density, right? So now the average quantization noise power at the output of the filter, at the output of this filter, would be 2 times w, the area under this, right? If I pass this signal, if I pass the noise signal through this filter, I'll get the power or noise power, quantization noise power at the output of the filter is 2 times, that is minus w to w, right? So 2 times w into this is nothing but the power spectral density of the quantization noise, and it is as good as w into delta square into ts divided by 3. This 2 divides here 3, right? So w into delta square into ts divided by 3. So therefore the SNR, signal to noise ratio, or signal to quantization noise ratio of the filter at the output of the filter is nothing but signal power by noise power, right? So I can say this delta square divided by 8 pi square, right? 8 pi square f naught square, right, into ts square divided by, so this is the signal power, and this is the noise power at the output of the filter, w delta square ts divided by 3. Or further, if I simplify this, I'll get, so this delta and delta getting cancelled here, right? Delta square getting cancelled. The step size do not exist. The delta does not exist. And if I simplify this, I'll get 3 divided by 8 pi square w f naught square into ts cube. Okay, into ts cube, right? Any doubts here? Any doubts? Ariman? Any doubts, Ariman? Are you there?
No doubt, sir.
Sayani? Are you there? Then again I will have to ask Yuvraj. Yuvraj, are you there?
Yes, sir.
Yeah, yeah. Any doubts? Any doubts, Yuvraj?
no, sir.
I'll proceed then. Okay, so now the signal to noise ratio, we have already obtained this, right? So signal to noise ratio is nothing but 3 divided by 8 pi square W F naught square into Ts cube, Ts cube. So if we measure it in this decibels, right? 10 log dB, right? 10 log SNR, if we do, we'll get there will be 9 dB improvement in the SNR with doubling of the sampling rate. Now, if you double the sampling rate, that means what? You double the sampling rate, that is Fs equal to 1 by Ts, right? If you double the sampling rate, you will find 9 dB improvement in the SNR. So higher the sampling rate, better the SNR, right? So this is what you can conclude from this delta modulator system. Okay. Any doubts with this? I have completed baseband modulation part, delta modulator part. So I have solved this example. This is there in the book also. You can refer this example to understand the problem that I have given in the notes. Notes in the sense I just uploaded on I think on Tuesday, right? You can refer the third problem. I mean, you can solve the third problem with the help of this. Okay, if you go through it properly. Okay. Now I'll go back to QPSK. So we have seen the QPSK is a quadriphase shift keying in which uh, face of the carrier contains information. So information is placed in the face of the carrier, right? What is information here? Not just a binary bit, it is a debit, right? So two binary bits together forming one symbol, two binary bits together, one symbol, that is debit. Okay, so if we combine two binary bits together, that is 0 and 1, right, we can have four possible combinations. One is 0 0 0 1 is the other one, 1 0 is the third one, and 1 1 is the fourth combination, right? So we can place these information, these symbols in the face of the carrier and transmit, right? We have seen the constellation diagram in the last class, that we can represent a signal vectors in a two-dimensional vector space, right? As there are two basis functions phi1 of t and phi2 of t. Phi1 of t is nothing but in phase carrier, that is square root of 2 by t capital T cos 2 pi fct, right? And quadrature carrier, that is phi 2 of t, is square root of 2 by t, right, sine 2 pi fct. Now this t, capital T, is nothing but the duration of this symbol, right? Capital T is duration of this symbol, right? So combining two symbols, if I have a binary symbol of duration tb, right, one symbol of duration tb, combination of two binary symbols together as a debit will have a duration t. Now this capital T is nothing but 2 times tb. Okay, right? So we have seen in the last class the BPSK transmitter. So what you observe in the transmitter here, so there will be an in-phase system and quadrature system. So do you know what this, if I consider only this part, what it is? What it is actually, if I consider only this part here? Can you tell me, Yuvraj?
So there will be all the, I think, odd bits of the input
Yeah, what
NRZ.
you consider, what you call this system as, only if I take this system separately out.
Sir, amplitude modulation.
Right. It's a BPSK system, right? It's one BPSK, that is binary phase shift keying, isn't it? Right? If symbol is one, symbol one, in polar NRZ format, it will be right. Its energy will be multiplied by this signal, right? Now, if the symbol is 0, right, the polar NRZ form will be minus of the signal, right? Minus, negative, and you will have a minus of the amplitude of the signal into square root of 2 by t cos 2 pi f ct, or I can say square root of 2 by t into that amplitude into cos 2 pi f ct plus pi, isn't it? So this one six system, or this part of the QPSK can be considered as BPSK. Also, this part as another BPSK system, right? Yes or no? Two BPSKs, right, connected in this fashion to form QPSK. Do you agree? Do you agree? Two
Yes, sir.
BPSKs, yeah? Yes or no? Yuvraj?
Yes, sir. Understood.
Yeah. So two BPSKs are connected in this fashion, right? Two BPSK, right? So two BPSKs. So what happens here? Bit sequence will be coming one after the other, 1 0 1 0 1 1 1 0 and so on. So the first bit will come here. Next bit will come here, right? Third bit will come here. That means say odd sequences are going to go to the upper BPSK, and even numbered sequences are going to come down to lower BPSK part. This is what is QPSK. I mean the combined these BPSKs. If I combine these two BPSKs and add them, it will be nothing but a QPSK signal. Okay, right. So now we will see the signal. How is it going to, right? We'll take the information. How is it going to modulate the carrier, and it will generate a QPSK. Let us see, right? So this is the binary sequence. I have 0 1 1 0 1 1 0 1 1. Now upper BPSK will latch on to these. Okay, will work on these, and the lower BPSK will work on these. Okay, alternately lower BPSK, right? So upper BPSK will take odd numbered sequence 0 1 1 0, and lower one 1 0 0 and 0. Okay, right. Now let us take the odd numbered sequence in the sense upper BPSK, this one. Okay, so you can see when 0 comes, the amplitude is taken to be negative here, and as the amplitude is negative, the carrier, right, gets multiplied with it, right, with it will result in a amplitude, I mean the sinusoidal signal like this. Okay, right. And similarly here for the symbol 1, the lower one is having the carrier sine 2 pi fct, right? So it will start as a sine 2 pi fct multiplied by the amplitude which is positive, and it will give you the sinusoidal signal here. Now this is the sampling interval, this is the interval of the symbol QPSK symbol, I can say, right? This is the interval for BPSK symbol is a B, and this whole two symbols together will have a interval T, right? Time duration T. It is QPSK symbol duration, right? So now here at this point, right? So you have two signals appearing, right? So this sequence, this binary signal is going to modulate the carrier here, right? And this one 0 here you can see is going to modulate the carrier like this, right? And so on, right? And the combined effect. So this is one BPSK, this is one BPSK, this is another BPSK. Adding these two will result in QPSK. Okay, adding these two will result in QPSK. Okay, right. So this is about QPSK modulation, right? So what is the feature of this QPSK? Now, if you are given a bit rate of 1 by TB, right, QPSK wave requires half the transmission bandwidth. So this is very important. Half the transmission bandwidth of the corresponding binary wave requires for BPSK. Binary wave requires half the transmission bandwidth of the corresponding BPSK. So it repeated, right? Corresponding binary wave, you can say corresponding bandwidth of the corresponding binary phase shift keying, right? Right. It requires half the bandwidth compared to half the bandwidth that of BPSK. Okay. Any doubts here? If no doubts, we move on to the next modulation technique, non-coherent modulation technique. Okay. So we'll be discussing only two of the non-coherent modulation techniques here. One is non-coherent binary frequency shift keying. Other one is non-coherent differential phase shift keying. Okay, so binary frequency shift keying, and other one is differential phase shift keying. Now begin with binary frequency shift keying. So you know binary frequency shift keying, right? So if the binary symbol is 0, carrier will take one frequency, and if the binary symbol is 1, carrier will take another frequency, right? So the two frequencies are taken such a way that they are orthogonal to each other in a symbol duration, right? So we can define the modulated carrier for binary frequency shift keying. Si of t is equal to square root of 2EB by t sub b cos 2 pi fi of t, 0 less than or equal to t less than or equal to t sub b. Duration of this signal is tb, right? And it is 0 elsewhere. And as there are only two binary symbols, I can take value 1 and 2. So 1 stands for maybe symbol 0, 2 stands for symbol 1, or you take it any way you want. 1 stands for symbol 1, 2 stands for symbol 0. Okay, right? So F1, let us say, is the carrier frequency for symbol 1, and F2 is the carrier frequency for symbol 0. Right? Now the block diagram. So now you have so far you are aware of a coherent modulation scheme in which you find bank of correlators at the receiver, right? Bank of correlators at the receiver. In the case of BPSK, you have seen in that you have one correlator, right? One correlator. And in the case of BFSK, you have two correlators. Even in the case of QPSK coherent modulation scheme, you have seen two correlators, right? Bank of two correlators. Now, when we say system or the modulation scheme is a non-coherent modulation scheme, there is no reference carrier at the receiver. There will not be taken a carrier frequency, or there will not be carrier frequency generated at the receiver, right? And we use a matched filter. In this case, binary frequency shift keying non-coherent modulation scheme, receiver do not possess bank of correlators or correlators. Receiver will have only matched filters here, right? So because there is no generation of local carrier or the carrier at the receiver, right? So now there are two matched filters required here. Matched filter matched to the basis function phi1 of t, right? Phi1 of t, and another matched filter matched to the basis function phi2 of t, right? We are not actually generating the carrier here. In fact, we are taking system whose response is matched with the transmitted signal, right? So phi1 of t, but the duration of the filter is having the impulse response. I can say impulse response is defined from 0 to t, right? So matched filter, you know what it does, right? It takes the signal, right? It convolves the signal, right? And if it matches with the signal at the sampling interval, you will find it giving the maximum value, and the envelope detector is just here to retain the envelope, right? So because information is, right, contained in the envelope, we can say here, right? So then it is sampled every t sub b, so envelope detector is just to retain the envelope of the carrier, because when you just convolve the incoming signal with the matched impulse response, right, at time t sub b you have a maximum value with respect to this filter. So you can see it every sampling interval, right, t sub b, if the signal is corresponding to symbol 1, you will get a maximum value here, and if the symbol is corresponding to match filter 2, it will be giving you maximum value here at time t equal to maximum, in the sense maybe negative here in this case, right? So now L1, right, if L1 is greater than L2, right, if L1 is greater than L2, L1 is the signal goes, the common signal goes to upper filter as well as lower filter, and if this results in L1 and this sampler results in value L2, and if L1 is greater than L2, right, the symbol is corresponding to the transmitter symbol 1, right? If L1 is less than L2, if L1 is less than L2, it is 0, okay, it is 0. So the reason is, if 0 is modulating the carrier and it is transmitted over the channel, it comes here, and both these match filter get the same signal, and as 0 signal corresponding to 0 is matched with this filter, you will get a maximum value at the sampling interval TB here. And if the symbol 1 modulates the carrier and it gets transmitted over the channel, noisy channel, the same signal comes here, the signal comes here, both the match filter will take the same signal, and if the transmitted signal is 1, you are expected to get maximum value at time t equal to t sub b here, and this results in L1 greater than L2 if the transmitted symbol is 1, and if the transmitted symbol is 0, it results in L1 minus L2, less than 0, right? L1 minus L2 less than 0, right? If the channel is noisy and 0 is transmitted, let us say, and due to the noise, if you get L1 greater than L2, the receiver will decide the symbol as 1, okay? That causes an error. That is going to result in an error if there is more noise in the channel, right? So we can define. I'm not going to take up the analysis for this error analysis for this particular modulation scheme, that is non-coherent modulation scheme, whether it is BFSK or DPSK, right? The probability of error I will define directly as half times e to the power minus EB by 2n naught, right? Half times e to the power minus EB by 2n naught is the average probability of error, assuming the symbols emitted by the binary source are equiprobable. Okay, any doubts? Any doubts? Yuvraj?
No doubt, sir.
Next, we move on to differential phase shift keying. Right? It's again one more non-coherent modulation scheme. Differential phase shift keying. It's a phase shift keying, but it is also a differential phase shift keying. It's a non-coherent version of phase shift keying. Just a non-coherent version of phase shift keying. There are two things here done in the differential phase shift keying, right? So what it does is it eliminates the need for coherent reference signal at the receiver by combining two basic operations at the transmitter. There are two basic operations in this particular scheme. One is differential encoding. Because of this, just because of this, right, we do not require a reference of the reference of the carrier at the receiver, right? Differential encoding and phase shift keying. Phase shift keying anyway is somewhat similar to binary phase shift keying, but the differential encoding is quite different, right? So in this case, what we do is to transmit a symbol 0, phase advance of the current carrier is already sent, let us say, right? Current carrier is already sent, let us say. Now, if the next symbol I need to transmit a 0, I have to advance the phase of the already transmitted signal by 180 degrees, right? 180 degrees. So I have to advance the phase by 180 degrees if I want to transmit a 0. That means, say I have transmitted the carrier, say cos 2 pi fct, for some symbol, whether it is 0 or 1. Now, if I want to transmit 0, I have to advance the phase of it, that is cos 2 pi fct plus pi. I have to transmit the carrier by advancing the phase of the previously transmitted signal. Now, to transmit a symbol 1, phase of the current signal will remain unchanged, right? So now I have already transmitted signal, let us say cos 2 pi fct, right? I have already transmitted a carrier signal cos 2 pi fct for some symbol, okay, whether it is 1 or 0. Now, if I want to transmit 1 again, I will transmit cos 2 pi fct again for this symbol 1. I will not change the phase of it. I will transmit it again. That results in now, if even though the symbol is of duration tb, right? That even though the symbol is of duration tb, if I have to transmit a symbol, it depends on the symbol which I have to transmit, so that I can change the carrier. It will take 2 symbol durations. Automatically it will take 2 symbol duration, I can say, right? So the receiver equipped with a storage capability to measure the relative phase difference between 2 waveforms received during the 2 successive. Now, the 2 successive bit intervals come into picture. That is the reason why we say it is for 2 symbol interval, right? So this is possible. This can be possible only if unknown phase, due to distortion, there is a possibility that phase theta may vary, right? We expect phase do not vary much, or very even if it varies very slowly, we expect this phase be approximately constant throughout, right? Now let us see the analysis, right? S1 of t denotes the transmitted DPSK signal, right? So why we have to consider for 2 symbol duration, right? We have to take past symbol which is transmitted, and to decide the phase we have to take the present symbol as well. So that is the reason why it comes under 2 symbol duration, right? So S1 of t is nothing but square root of EB by 2 TB cos 2 pi fct, right? Say first signal, let us say, is sent over a symbol duration t sub b. Now, if I have to transmit the symbol 1, if I have to transmit the symbol 1, I have to send the same signal again, right? I have to send the same signal again without changing the phase in symbol interval TB to 2 TB. This you please focus on. If I have already transmitted the signal for either 0 or 1, right? If my current symbol is 1, I have to repeat the transmission. Whatever I have transmitted in the past should be transmitted again for symbol 1. That is the reason why total symbol duration for one symbol we consider as 2 TB. Okay. Similarly, for symbol 0, right? Symbol 0, S2 of t, if already transmitted signal is, say, square root of EB by 2 TB cos 2 pi fct for a symbol duration TB, when duration of TB, right? If I am transmitting a symbol 0 now, in this duration I have already transmitted. After TB, if I want to transmit a 0, right, I have to advance the phase of this transmitted signal by pi and transmit it, right, in the symbol duration TB to 2 TB, right? So in the next symbol duration I have to transmit, okay, next symbol duration I have to transmit 0 by advancing the phase. Okay, any doubts here? Any doubts?
No, sir.
Yeah. So modulated signal S1 of t for symbol 1, right? If you want to transmit the symbol in TB to 2 TB, you have to transmit the signal or repeat the signal what you have transmitted in first symbol interval. Okay, and in the case of transmitting a 0 in the duration of TB to 2 TB, you have to advance the phase of the already transmitted signal by pi. Okay. What is differential? We'll see before that DPSK transmitter, right? So DPSK transmitter looks like this. So you have input binary sequence, right? Binary sequence, right? So binary sequence in the sense 1 and 0, 1 0, 1 1 1 0, and so on, right? So it is applied to a logic network. What this logic network, we will see, it is nothing but the XNOR operation, right? XNOR operation. What it does actually, logic network gives out an output, and this output is delayed by T sub b. That means what? If my signal present binary bit is BK, it will be XORed with past output of the logic network, past output of the logic network, right? Past output of the logic network, if it will be delayed by T sub b, right? So if my present bit is BK, right, it will be XNORed with past logic network output, which is nothing but the XNOR, okay? And this will generate binary sequence. Now this one is amplitude level shifter depending on the signal. If it is binary 1, right? If it is binary 1, value plus 1, I mean plus v. And if it is not a binary, if it is not a if not a 1, if it is 0, it will be advanced by pi. Okay, so that means what magnitude will be minus. Okay, so let us take an example, right? Let us assume this binary sequence is 1. Binary sequence is 1 0 0 1 0 0 1 1 here. So I have drawn the table. You can see the binary sequence. First bit is 1, second bit is 0 1 0 1 0 0 1 1, let us say. And differentially encoded sequence D sub k is nothing but differentially encoded. Differentially encoded in the sense what? The past bit output of the logic network, past output of the logic network is differentially encoded, I can say. So D sub k is nothing but bk XNOR with dk minus 1. Okay, and let us, if I consider past bit is already 1, okay, let us say past output is 1 for the time being, right? What will be the present output? 1 XNOR 1 must be, Yuvraj? 1 XNOR,
It should be
yeah,
one.
yeah, it must be 1, right? 1 XNOR 1 must be 1. Now the present bit, for present bit 1, right, present output is 1. Now the next bit I take, present bit is 0. What will be the past of output? It will be 1, right? 1. So it is nothing but XNORed will result in a 0, right? So next, what do you expect the output here? When the input is 0 here, what is the output? Sagar, 0 XNOR 0 is 1, right? And so on, right? 1 XNOR 1 is 1, 0 XNOR 1 XNOR 0 is 0, and rest you can see, right? And verify. Okay. Any doubts here in this sequence? This is nothing but a differential encoding. First, there is a differential encoding in the DPSK system, then phase shift keying, and this part here is differential encoding, and this is nothing but BPSK. This part is nothing but BPSK. Okay, so now next, so what is the transmitted phase then? So phase, if the current signal is, if the current signal is 1, transmitted phase must be 0. That means what? Signal must be retransmitted as it is without change in phase. Now if the current signal is 1, right, the transmitted signal must be with the phase 0, no phase change. Now what about this? If the current signal here is 0, what will happen with this transmitted phase? Can you tell me, Sagar? What will be the phase? Sagar, are you there? Sagar Reddy? Can you tell me, Shafwan? Are you there? Sayani? No one? Yuvraj?
Sir, we should get pi here.
Yeah. You only attend or what? They just simply log in and leave or what? Huh? Sorry. We should get we should get pi here, right? So we should get pi here. And if the input signal now is 1, we should get 0, 0, right? The input signal is 0, we should get pi. Rest are 0, 0, and 0. Any doubts here? So what you understand by this? There are two steps in this differential phase shift keying. One is differential encoding. Differential encoding is done here, right? This is the differential encoding part, right? Differential encoding part, right? Differential encoding is nothing but XNOR operation. Present bit XNORed with the past output of the XNOR gate, right? So it is simple XNOR gate it is used here, and there is amplitude level shifter. If it is 1, phase is not going to change. If it is 0, phase is going to be pi, right? So negative value, phase is going to be pi. This part is nothing but phase shift keying or binary phase shift keying here, right? Right? Any doubts?
Sir,
Yeah.
so for transmitted phase part, we are applying XNOR also there, no?
Where?
Are we doing XNOR at the transmitted phase part also, or just we are seeing with the past input?
So now what this output is binary data now, ones and zeros.
Yes, sir.
Okay, ones and zeros, again a binary data, right? So only this part up till here it is a differential encoding.
Okay, yes, sir. Yeah.
Okay, after this differential encoding, ultimately what I'll get, binary data only I get. Okay, I get the binary data only. Okay.
Yes, sir.
You consider this to be binary data. Instead of considering this to be binary data, this I am considering as binary data now, only after differential encoding. So advantage here is, advantage of going like this is I don't require carrier reference at the receiver, right? Carrier reference at the receiver, I don't require that, right? So how we can receive it, let us see. Right, we are encoding before, just this you can treat as if it is a BPSK transmitter. Okay, this one, this whole thing, this whole thing is a BPSK transmitter, whereas this part is only a differential encoding. That is the only difference. Differential encoding first, then comes the BPSK, binary phase shift keying, right? So after doing this, after differential encoding, right, then only we are going for BPSK. So how we do differential encoding? Just XNOR the present incoming bit with the past output of the logic network. That is XNOR output. That is the only thing. Okay, right?
Yes.
I hope your doubt is cleared.
Yes, sir. So, but then, where we are getting pi, sir. So, is it due to the phase change? Since we have one input
See here,
already.
0. I get 0 here, and if I take this 0 pass through a level shifter, now if I consider NRZ polar format, what I'll get?
So be minus,
Negative amplitude, right?
yes,
Some
negative,
negative voltage I'll get multiplied by this,
yes, sir.
or it is as good as here. Like for 0, it is as good as some positive voltage into square root of 2 by t sub b, right? Cos 2 pi fc t plus pi, right?
Pi.
Yeah.
Yes, sir. Yes, sir.
Yeah. So that is the only thing. That is the only thing. So 0. This is nothing but BPSK only. Okay. Why we are doing? Why we are performing this? We are performing this at that is differential encoding is to avoid carrier reference. If it's to avoid generating the carrier signal. How is it? Let us see. Right, block diagram of a DPSK receiver. Right. So I get the incoming signal x of t. Right. I get the incoming signal. I will strictly band limit that x of t. Right. I'll keep that this is in the band. Right. Then I will delay it by t sub b, because the duration of this signal is t sub b, right? Delay by t sub b. Then I will have one more signal coming here, right? Right? If this delayed signal is, if this delayed signal, say cos 2 pi fct, is same as incoming cos 2 pi fct, right? If delayed signal is same as incoming cos 2 pi fct, then what they get multiplied here, right? They get multiplied here, and then if it is passed through, a correlator, right? We are not using a matched filter here because indirectly we are generating a carrier here. So it is multiplied by, it is cos 2 pi fct are getting multiplied and passed through an integrator. It is nothing but a correlator here, an integrator. What is going to happen if I multiply these two signals? If I multiply cos 2 pi fct and cos 2 pi fct and over an integral 0 to tb, the integral over at 0 to tb, what I'll get? Some positive value, isn't it? Yes or no? Yes or no?
Yes, sir.
Assuming there is no noise for the time being. Assuming there is no noise, there is no phase variation, right? Cos 2 pi fct multiplied by cos 2 pi fct, right? This circuit as if a correlator, right? It's a correlator. In fact, I am not using a matched filter here, right? We are not using a matched filter here. Correlator, in fact, cos 2 pi fct multiplied and passed through an integrator will give you a positive value, right? Will give you a positive value, right? Let us say if this is positive value, what is the decision? What is the decision will be made, right? Decide in favor of symbol 1. Let us say the incoming signal is cos 2 pi fct plus pi, and the past signal already entered here is cos 2 pi fct, right? Multiply these two, integrate through 0 to tb, what I'll get? Can you tell me, Yuvraj? Past signal is cos 2 pi fct, present signal is cos 2 pi fct plus pi, phase advanced by pi. What do you get?
We should get a negative value.
Negative value. That means what? It is 0, right? This is what the advantage of using differential encoding at the transmitter, right? You get 0 and decoded, right? So if both are past values, right? Both are this. Is it possible?
Sir, it should be possible.
Yeah. Then what will be the resulting signal?
1.
1, huh? So past signal is 0. Next signal is, if it is 1, right? Next signal, if it is 1, phase won't be changed, right? Phase won't be changed. It will be transmitted as it is. Cos 2 pi fct pi was transmitted in the past because it was 0, right? If the next symbol is 1, cos 2 pi fct plus pi is transmitted again, will be transmitted again, resulting in a value equal to 1. That means what? This transmitted, this received signal corresponding to symbol 1, right? Yes or no?
Yes, sir.
Yes. Okay. So this is about the differential phase shift keying, right? So we are again not going through the analysis for probability of error in the case of differential phase shift keying. Probability of error in this case is half e to the power minus eb by n naught. Let us just recap of what we have studied in different modulation scheme. See here, we are not discussing MSK here, minimum shift keying we are not discussing. We have discussed binary PSK, coherent binary PSK. We have discussed coherent QPSK. We have discussed coherent and non-coherent binary frequency shift keying, and also we have discussed DPSK. There are many more modulation techniques, right, such as minimum shift keying, and there are Emery modulation schemes. Emery QAM we have, right? Emery PSK we have. So one of the Emery PSK is coherent binary PSK, right? We have studied, and if you want to have more and more information regarding this, you can refer a textbook that you have already downloaded, right? Digital communication systems. In that also you can find, or in the book Introduction to Analog and Digital Communication by Simon Hakim. Okay, now you can see the probability of error, bit error rate, right? Probability of error in the case of coherent binary PSK, QPSK, coherent MSK, right? It is it is about half ERFC EB by square root of EB by N naught, isn't it? Yes or no? Or if you have any other value, coherent BPSK. What about the probability of error in coherent QPSK? Yuvraj?
Sir, it is same only.
Is it same or half is not there?
Yeah, it's double. Sorry, it is double. Half is not there.
Do you think this half will matter much? In the case of QPSK or PSK, half will matter much if you have very high signal to noise ratio.
No, sir.
It is, you can say QPSK is as good as almost half ERFC of square root of EB by N naught, right? So if I have a probability of error 10 to the power minus 9 in the case of BPSK, in the case of QPSK, it will be around 10 to the power minus 9 divided by 2. That's all, right? It is 0.5. It is a 0.5 into 10 to the power minus 9. That's all, right? Right? It's not much, right? So you can say, so that is the reason why they have taken half ERFC. It will not make much difference as far as coherent PSK is concerned, right? And as far as coherent binary FSK is concerned, half ERFC, right? You have already worked on it. Square root of EB by 2 N naught. DPSK has half e to the power minus EB by N naught. Coherent binary FSK has half e to the power minus EB by N naught. Right? You can see the probability of error versus the signal to noise ratio EB by N naught curve, right? EB by N naught curve, right? Comparison of different modulation scheme, right? You can see, right? You can see the bit error rates for all the modulation, all the systems decrease monotonically. You can see as you increase the SNR, you can see the bit probability of error decreases exponentially. We can say monotonically with increasing value of EB by N naught. The defining curves have a similar shape in the form of waterfall. You can see it looks like a waterfall here, right? For any value of EB by N naught, coherent PSK, QPSK, MSK is minimum shifting, produces smaller bit error rate than any other modulation scheme, right? So smaller bit error rate. So you can see, you can think these three modulation schemes which are discussed here are coherent modulation schemes. Okay, just because they are coherent modulation scheme, they have less probability of error compared to other modulation schemes, right? Coherent binary PSK, DPSK require EB by N naught that, right, is 3 dB less than corresponding values for conventional coherent FSK, right? So the coherent binary PSK and DPSK require EB by N naught that is 3 dB less than coherence corresponding values for conventional coherent FSK and non-coherent binary FSK respectively, right? So these are the many points. You can just make a note of it, right? These are there in the book. You can just go through, right, and read. Any doubts so far in the modulation schemes we discussed?
No, sir.
Shafwan, Aryaman.
No, sir.
You are able to follow it now? You are able to understand? Are you, Yuvraj?
Yes, sir.
So with this we have completed modulation schemes. Okay, passband modulation scheme. Next we will move on to information theory and coding. So the objective of this topic is to quantify information. Quantifying information, not only quantifying information, we go for coding the information. Then we go for transmitting the information. To transmit the information, we need channel. So we quantify the channel as well, right? So information theory and coding we discussed, the main objective is to quantify information, quantify the channel. Okay, right? So far, with the knowledge of digital communication and analog communication, what we understand by probability of error and how to minimize the probability of error in communication. How to minimize the probability of error in the communication?
Sir, increase SNR.
That is the impression, increasing the SNR. You need to increase SNR. Do you think you can increase the SNR as much as you want?
No, sir.
So there is a constraint. So if you are a designer of a digital communication system, or if you transmit signals using your system, you are supposed to be abide by the rules and regulations framed by the governing body with respect to communication, right? So you cannot transmit a signal beyond signal power beyond a level, right? Beyond certain level, right? So you are restricted to transmit your signal in certain applying. I mean, you are bound to transmit the signal with certain power. You cannot exceed that power. If you exceed that power, you will end up in disturbing others' band. You will end up in disturbing others' band. They will file an objection against you, and you will be sued for transmitting the signal with the power exceeding the limit. Okay, right? So we know that this probability of error is proportional to ERFC. As Yuvraj said, we need to increase the signal to noise ratio to minimize the probability of error. So we know this energy Emax is nothing but Pmax into T sub b, where T sub b is nothing but the duration of the symbol, and we can say this Pmax is nothing but Emax by T sub b, or 1 by TB we know as bit rate, right? So we can say Emax into RB, right? So we are supposed to transmit a signal with some maximum power. We cannot go beyond that. What we can do here on the right hand side, so that we transmit the power Pmax, but we want to achieve minimum probability of error. What we can do is we can increase Emax, but we need to decrease bit rate, right? If we increase bit rate, we need to decrease Emax, right? This is what is the problem, right? What was the impression in early 1940s, that if you want to transmit the information without any error or minimum possible error, you need to increase the signal to noise ratio, as Yuvraj said, right? As Yuvraj said, right? We need to increase the signal to noise power, but we cannot do that, right? So how we can minimize the signal, minimize the probability of error? So that we have to learn from the information theory itself, right? So we are not permitted to increase the signal power to a level we want, right? So the designers were under the impression that to increase or to reduce or to decrease the probability of error, or to minimize the probability of error, we need to increase the SNR, right? It was until 1948, right? It was the impression. Now the Shannon's, at that time in the year 1948, Shannon published a paper called Mathematical Theory of Communication. What is said in that? There was two questions in the paper. There were two questions before this paper. One was, what is the rate below which information cannot be compressed, right? His paper answered it as an entropy. The rate below which information cannot be compressed is entropy. You cannot compress any data below this value, that is entropy. You cannot compress the data. His paper answered the question. Before his paper, there was a question: what is the rate below which you cannot compress the data? It is entropy below which you cannot compress the data. The second question was there before his paper came into picture, was what is the rate above which, right, information cannot be transmitted without any error, right? So he answered, our intention was to reduce the probability of error by increasing the SNR, right? So what is that value? What is the rate above which we can we cannot transmit the information, without any error. So that is answered by the paper. It is channel capacity. What channel capacity says that is we can transmit the information without any error, or error that we want, as small as possible, or as small as we want, right? Error as small as we want, we can transmit if the rate of information transmission is less than a value called channel capacity, right? Channel entropy says we cannot compress the data below a value entropy, right? We cannot transmit information at the rate above a value called channel capacity. Now this is lower bound of information theory. And this one is upper bound, of information theory, right? And this theory, information theory, valid even today, right? Based on this paper, right? If his paper was not there, people were under the impression you just increase the signal to noise ratio. Now if you keep increasing the signal to noise ratio, you would trouble others band. We wouldn't have many systems existing, right? Because of his paper, we came across the thing that we can transmit a signal or data without any error, or error as small as we want, right? As long as the rate of information transmission is less than capacity, right? So this entropy is one number, channel capacity is another number. That means these are numbers, these are quantified, right? So these are numbers and these are quantified, and we just say information theory, right, is nothing but quantification. We just quantify information here, whether it is quantifying the information with respect to the source or anything, and we quantify the channel also. We quantify the channel. We just give some number to this, right? We just give number. We define some number for this, right? So that is entropy for source, channel capacity for channel, right? So these two, entropy is a lower bound in the information theory, channel capacity is an upper bound in the information theory. Any doubts? Right? Hello, Yuvraj?
No doubt, sir.
Yeah.
No doubts.
Yeah. Right. That means entropy is some value, channel capacity is some value. That means we need to have some quantification. We need to quantify the information, right? We need to quantify the information, right? So before that, we will just see the Shannon's model of a digital communication, right? So we just see the Shannon's model of a digital communication. So there is an information source, right? So information source is a discrete information source, right? Discrete information source, and the output of this source can be symbols, right? What this source can be, right? It can be a binary source, right? It can be source with some n symbols, right? So if I talk about a quantizer, say uniform quantizer with some L representation levels, I can consider this uniform quantizer as a discrete information source with L symbols emitted by the source. Now, if I say uniform quantizer is a memoryless source, right? What do you mean by memoryless source? Any idea? Memoryless means what? Any source which is memoryless?
Sir, it means that the source is not aware of any previous values of information it has transmitted.
That means what? Source emitting values are independent, right?
Yes, sir.
It will, the symbol emitted by, or the value emitted by the source, right? If I say quantizer, right, L equal to, if I have a uniform quantizer with L equal to 16, the source will have 16 symbols, right? And these symbols get emitted depending on the input sample which is coming to it, and accordingly it will approximate to nearest, right, representation level, and it gets emitted. That's all. Right, it is right, and the next symbol which comes will not depend on the symbol which is already occurred, or will not depend on the symbol which is going to occur next, right? So a discrete information source, the source get emitted by the, information source emits symbols. Example of this source can be a binary source which emits binary ones and zeros. Example of this source can be a quantizer of some L number of levels, right? And output of these source is to be encoded, right? So it requires a binary representation for this source symbols, right? It requires a binary representation for this source symbols. Now we will study the source encoder also, will study the information source also. Now the symbols or the values emitted by the information source get encoded by the source encoder, right? It's a binary encoder, right? And it is passed to the channel encoder, right? The purpose of channel encoder is to, right, is to get safety from the noise in the channel, right? Get safety, get secured from the noise in the channel. Now the purpose of source encoder here is to have minimum redundancy. Purpose of this source encoder is to have minimum redundancy. Purpose of channel encoder is to add redundancy. Okay, so we'll come to know this. Purpose of source encoder is to have a minimum redundancy. That means we want to have a code as short as possible, and purpose of channel encoder is to have more redundancy added to this encoded output, so that the channel, right, channel, even if it affects the signal, binary signal at the receiver, we can use some techniques at the channel decoder so that we can correct any error if any, right? And the output of this decoder is passed through a source decoder. Source decoder, what it does, it will just assign quantized levels back, or just recombine the signals and give the destination. Give it to the destination. If you want to store it, or if you want to send it to the output, right, it is left to the designer of the system. This is Shannon's model of a digital communication system, right? What will be our focus in this topic is information source, source encoder, and channel. Okay, information source, source encoder, and channel. And we will touch upon this channel encoder to some extent. We'll just give a brief introduction to this channel encoder. We'll not go into detail, right, of this channel encoder. Right, our main focus will be on source encoder, channel. Right now, to encode these symbols of a source, we need to have the information measured, right? So source emits some symbols or the values. We need to measure this so that we can encode it. Okay, we need to measure it so that we can encode it. So measure of information. Measure of information is very, very important. That is quantifying the information, right? Yeah, Yuvraj, tomorrow is Friday, right?
Yes, sir.
And tomorrow is Gandhi Jayanti too. Yes, sir. Yes or no?
Yes, sir.
Shall we have a class tomorrow, extra class? Yuvraj? Yuvraj, are you able to hear me? Shall we have extra class tomorrow?
Sir, it's not my decision, sir.
Okay, it is not your decision. I made 3 statements now, right? You don't have to worry. I made 3 statements. One is tomorrow is a Friday. Another one is tomorrow is a Gandhi Jayanti and it's a holiday. And third one is tomorrow I am going to take the class, right? Tomorrow is a Friday. All of you are aware of it, right? Tomorrow is a Friday, right? There is nothing new in it, right? Tomorrow is a Friday. That means you all know it. It's a certain event. It's a sure event, right? It's a sure event. Occurrence is probability of occurrence is 1, right? It is no way that it cannot be, it can be other day, right? So it is Friday only, sure event. You gain no information, right, from me, that when I said tomorrow is a Friday, you know it, right? It's Friday. Why is it telling us Friday? There is no information. There is no information in it, in fact. Second statement I made, right? Tomorrow is a Gandhi Jayanti as well, right? 2nd October, we all know it, right? Gandhi Jayanti as well. Some of you might not be, I mean, aware of it, may be busy with some other work, may not be able to, right, know that it is a Gandhi Jayanti, right? For some of you, it is, right, just a reminder saying that it is Gandhi Jayanti, or some of you are aware of it. It is, right, to some of you who are not aware of it, right, that it is Gandhi Jayanti tomorrow and it is a holiday. Oh, they will come to know. Okay, I have a holiday anyway tomorrow, right? That means you get some, those who are not aware of it get some information, right? Right, that tomorrow is a holiday and Gandhi Jayanti. And third statement I made, shall I take extra class, or I will take extra class? If I say, Yuvraj did not answer only. He was surprised. He was stunned, isn't it, Yuvraj? It is not my alone's decision, he said, right? Yes or no?
Yes, sir.
You were stunned by my statement saying that tomorrow is going to be a class. If I say yes, my friends will hit me like anything after I come back to the college, right? So you were surprised. That's why you took some time, right? You took some time, in fact, right? Yes or no? To answer to this question, that tomorrow whether you will say yes or no, right? Right. So what about the third statement when I made? I made that tomorrow I'm going to take class. Possibility occurrence of this event is very less. Yeah.
So please no class, sir, tomorrow. We get one holiday once in a while, so.
No, I'm not taking class. I'm just telling you. Okay. Tomorrow I'm not taking the class. I'm telling you just to tell you with respect to information theory. You were surprised and you find you were suddenly got stunned. And then I say this event, chances of occurring this event or this thing is very less. Please mute your mic. Chances of occurring this event is very less. When I said, right, when I said you were surprised and the more information you got, that means the event which is least likely to occur contain more information. You were surprised, right? You were surprised. By third statement I made, contains more information. Event that occurs least likely contains more information. Event that occurs more likely, right, more likely, contain less information. Okay, less information. Event that is least likely contain more information. Event that more likely contain less information, right, less information. And event that surely occurs, event that surely occurs. Tomorrow is a Friday, means Friday only. It cannot be anything else. You know it. There is no information. You will not gain any information from it because you are aware of it, right?
Right.
If I say, right, tomorrow is a Thursday, then it is not a certain event. It is never going to happen, right? Occurrence, chances of occurring that event is 0, right? Saying that tomorrow is a Thursday, right? It's 0. That means you gain no information from it, right? The event that never occur cannot contain any information. Event which is more likely to occur contain less information. Event which is less likely to occur contain more information, and event which is very certain contain no information. Okay, so this can be applied to the source as well, discrete memoryless source. Now if you consider a discrete memoryless source, right, and let us say it emits symbol every unit of time, right, the source output is modeled as a discrete random variable s, which takes on symbols from a fixed finite alphabet s, right? We define a source alphabet s containing symbols S0, S1, and so on up to Sk minus 1 with probabilities, right? Probabilities, chances, I can say P of S equal to Sk equal to Pk. Pk we can define for k equal to 0, 1, 2 and so on up to k minus 1, summation k equal to 0 to k minus 1 probability k, total probability equal to 1 here, right? So our main intention is to quantify information. On what basis? On the basis of the chances of occurrence of symbols, right? The symbol which is more likely contain less information, symbol which is less likely contain more information, right? So let us see the measure of, right? So when we say a discrete memoryless source, right, symbols emitted by the discrete memoryless source are statistically independent, okay, are statistically independent. That means what, occurrence of a symbol does not depend on preceding symbol or successive symbol, next symbol, okay, right? We can say that symbol which is more frequent contain less information and a symbol which is less frequent contain more information. Sure event contain no information at all, right? That means probability of occurrence of an event equal to 1 contain no information at all. Also, any event that has no chance to occur contain no information. Any event never occurs, no information. Now we'll have a measure of how we can measure this information. Source emitting symbols, but we need to measure it so that we can, right, we can transmit, we can encode and transmit the signal, right? So measure of information. Let us say we have an event called E with probability P of E. If we are told that event E has occurred, then we say we have received I of E. I of E means information, right? I stands for information, E stands for an event, right? Information content of an event is I of E is equal to log 1 upon P of E. I have not put the base because I say in general it is units of information, right? So information content present in event E or information content I get about E when it occurs is log 1 upon P of E units of information. Now I can measure this, right? I can measure this depending on the log. I can put a unit depending on the type of log, base of log I am using it, right? If I use log to the base 2, I say information content of the event E is log 1 upon P of E to the base 2 bits of it. Again, log to the base 2 1 upon PE bits of information regarding the event E. Now if I take the logarithm to the base E, I say I get log to the base E 1 upon P of E nats. I get nats of information for information event E, right? I get, if I take log to the base 10, I of E is equal to log to the base 1 upon PE is in Hartley's if I measure the information in log to the base 10, right? So information is measured in log 1 upon P of E, right? So P of E is the probability of occurrence of an event E, okay? Probability of occurrence of an event E is P of E, and measure, if once that event occurs, I say I got log 1 upon P of E, right? Units of information. For our digital communication, which deals with binary information, which log we need to take, Yuvraj?
Sir, base 2.
Yeah, log to the base 2. So we are interested only in this so far, right? In this, right? Log to the base 2, right? So the measure of information is in log to the base 2, right? Log to the base 2, right? So, right, probability, if probability of event equal to 0 or 1, we gain no information, we say I of E equal to 0. When event that never occurs will not have any information, even that certainly certain, very certain, whose probability equal to 1, and apart from this one no other event occurs, then it is, right, information about E is 0, okay? We gain no information at all, right? So now we define the average information content, or we call it as entropy, which is nothing but the lower bound in information theory, right? Information content of a source, or average information content of a source, right? Entropy, we define it as an entropy. So the source input, a source output model as discrete random variable S which takes on symbols from fixed finite alphabet, which we have already discussed, right? S equal to S naught. These are the possible symbols, let us say, right? So S is the source alphabet, S naught, S1, and so on up to K, K minus 1. There are K symbols, right? K symbols with probabilities of occurrence of a particular symbol. Sk is Pk, okay? Where k equal to 0, 1, 2, and so on up to k minus 1, and total probability equal to 1. Right? This we are aware of, right? So we define an average. I mean, to define an average information content of a source, we need source statistics. What do you mean by source statistics? We need to know what are the symbols, how many symbols, what are the symbols, how many symbols, and what are the probability of occurrence of these symbols. Okay. Now, and if symbol sk, right, symbol, one of the symbols, right, so one of the source symbols, right, one of these source symbols, if one of the symbols sk occur, right, we obtain amount of information about this symbol as log to the base 2 1 upon pk. So if the symbol occurs, we gain log 1 upon p sub k to the base 2 bits of information about this symbol. Okay, right, about this symbol. If the symbol sk occurs, we get log 1 upon pk to the base 2 bits of information. Okay, and we define the average on the average for entire. So this first equation what I have written is with respect to a particular symbol of a source sk on the average, right? What is the average information content if the source emits all these symbols, right? On an average we get summation k equal to 0 to k minus 1 pk I of sk, right, where k taking from 0 to k minus 1 bits of information. So we get bits per symbol, we get bits of information per symbol. We say h of s, that is on an average the information content we define on an average as entropy, right? So we define average information content of the source S as entropy of the source, and we define h of s equal to summation k equal to 0 to k minus 1 pk log 1 upon p sub k to the base 2 bits per symbol. We get bits of information per symbol, okay, per symbol. Okay, this is nothing but the entropy of the source. This I get bits for this information, I get bits for symbol sk, and this I get bits per symbol on an average per symbol. Okay, right? So h of s is a measure of average information content per symbol, is a measure of average information content per symbol of a source. Now let us take a discrete memoryless source with 3 symbols, right? Source S defined as S1, S2, S3 with probabilities P equal to 1 by 2, 1 by 4, 1 by 4. That means the probability of occurrence of S1 is 1 by 2. Probability of occurrence of S2 is 1 by 4. Probability of occurrence of S3 is 1 by 4. Okay. Now find the average information content of the source, or find the information content of each symbol, and hence find the entropy, right? Right. What is the average information content of symbol S1? I can say I of S1 is equal to log 1 upon P1. Log 1 upon P1 to the base 2. Okay. Log 1 upon 1 by 2 to the base 2. I'll get 1 bit of information. I get 1 bit of information about S1 when S1 gets emitted by the source. So I get similarly, I get 2 bits of information when S2 get emitted. I get 2 bits of information when S3 get emitted, right? So if I take individually symbol S1, once symbol S1 get emitted by the source, I gain 1 bit of information. Okay, 1 bit of information. If symbol S2 get emitted by the source or S3 get emitted by the source, I get 2 bits of information. Okay, and on the average, I get, if I take the entropy of the source, average information content per symbol, or information content per symbol, summation I k equal to 1 to 3 pi log 1 upon pi to the base 2. Okay, to the base 2 log 1 upon pi to the base 2. I'll get, if you simplify, you will get 3 by 2 bits of information per symbol. Okay, 3 by 2 bits of information per symbol. Now the average information content of the symbol is 3 by 2 bits per symbol, or average information content of the source we can say, right? It's a 3 by 2 bits per symbol. Yuvraj or any others, any doubts? Sagar Reddy, any doubts?
No, sir.
Did you understand?
Yes, sir. But I had some network issues, so I'll see the recording anyway, sir.
Yeah. Okay.
Excuse me, sir.
Yeah.
So when we evaluate these symbols, because the symbols are discrete, we can't say that we can get like 3 by 2 bits for every symbol, right?
On an average, I'm telling on an average. There is a difference. But wait, I will just.
Sir, I mean like application wise, we have to say something like we get 3 bits for every 2 symbols, or just 3 by 2 bits for every symbol.
On an average, I'm telling. On an average, I'm telling. Right, 3 by 2 bits per symbol. Right, on an average, it is on an average. Okay, right.
Yes.
Now, if I talk about a particular symbol, I say 1 bit alone. I get 1 bit of information. Right, on an average means. On the average, what is the now we will find this very important, this getting 3 by 2 or real number, I mean the fractions, okay, 3 by 2 or some 1.34325 like that. We will find it very useful, right, when we discuss coding, right? So this mainly our intention is to, right, get a code which is very short, as short as possible. And when we get a code, we talk length of a code. We talk like length of a code. When we say length of a code, we take the length of a code on an average. In that case, we may get value not in integer. We may get in fractions like this, 3 by 2 or something like this, right? We may get not as an integer, right, some other value, right? So we find this h of s, right? I'm just telling on the average bits per symbol, average number of bits per symbol. I get 1.5, right? Now when we are talking with respect to only few symbols. We talk usually with respect to the symbol rate at which information is transmitted, right? Symbol rate. What is symbol rate? Bits per second or samples per second, we say, right? Yes. In that we have millions of samples. Yes or no? Millions of bits, millions of samples, right?
Yes.
Right? Now, if I multiply this entropy by this, number of bits, right? Bits per second, right? Or you can say samples, right? So I can say samples per second, bits per second, right? This 3 by 2, right, will no longer be a real number. It will be a purely integer, right? For larger number, in the larger sense, if you see, right, in the broad sense, if you see, the source keep on emitting symbols, millions of symbols. This source itself, if you take, which has only 3 symbols, can emit millions of symbols after. I mean, S1 get emitted, S2 get emitted, maybe S1 afterwards, S3 then, right, and so on. Like this, keep on emitting. It emits S1, S2, S3, such that I will have millions of symbols emitted by the source, right? So we use this entropy to calculate the rate of the source emitting the symbol as well. Okay, when we come across the rate of the source, and if we multiply this 3 by 2 with those millions of symbols, that there won't be any fraction at all. It will be all integers. Okay, right? And we speak on an average. Okay, on an average, right? Whatever it is, whether it is integer or a rational number, whatever it is, right? Maybe 3 by 2, right? So we talk like that. So we on an average we speak like that. Okay, any doubts?
No, sir.
Yeah. Now the properties of entropy. What are the properties of entropy? Entropy is always a non-negative quantity. H of s is always greater than or equal to 0. H of s can be 0. It can not be less than 0, right? is always greater than or equal to 0, always non-negative. Okay, right? And this is the lower bound. Lower bound of entropy is h of s equal to 0. H of s cannot be less than 0. The lowest value of h of s can be 0. When it is possible, if the symbol, if any symbol has a probability equal to 0, or if any symbol has a probability equal to 1, okay, if symbol has a probability equal to 1, we say only that symbol occurs and the average information content about that source is 0. So entropy of a source symbol, right, entropy of a source with k symbols cannot exceed log k to the base 2 bits per symbol. Okay, right? So this is the maximum value, right? Maximum value of entropy. Entropy cannot exceed log to the log k, where k is number of symbols contained by the source, number of symbols in the source, right? H of s cannot exceed this log k to the base 2. If source symbols are equiprobable, then h of s equal to log k to the base 2. This itself is the maximum value. Okay, right? So this itself is a maximum value. Okay, h of s equal to log k to the base 2. Okay. Example. Let us consider a uniform quantizer with 8 representation levels. Let x be the input to the quantizer, which has a sample value, which is a sample value of a zero mean random variable x. Okay, right. What is the average information content of this quantizer if there is no overload on the quantizer? How many symbols this source can emit? If I take this quantizer as a source or a discrete memoryless source, how many symbols it has?
8 symbols, sir.
8 symbols. Now, if we assume there is no slope overload distortion, right, and uniform quantizer, that means what? The quantizer takes all possible levels, and we find the number of levels will lead in such a way that quantizer outputs are all equiprobable, right? So all, I mean, if there are 8 levels, all levels are equiprobable. If we take the reason for this is, reason for taking this is, now if I say sample value here x, if I have say sample value x be the input to the quantizer, and it is sample value of a zero mean random variable x, let us say, right, let us say we can assume we can assume the quantizer levels are all equiprobable. All 8 levels are equiprobable. We can assume that, okay, need not always be true, but let us assume that because of this x is a sample value of zero mean random variable. When I say it will take all from negative peak to the positive peak, it will take all possible values, and we say all these levels are equiprobable. We can assume, right? And if we consider x be zero mean, then we can say that quantizer has a source alphabet of 8 symbols which are equiprobable and independent. Independent because the quantizer we use is a memoryless quantizer, and we can define these levels, right? S0, S1, S2, S3, S4, S5, S6, and S7. These are voltage levels now. Okay, these are levels, right? These are levels. Now these levels are S0 to S7. Okay, where Sk is the kth discrete level, I can see. Then probability Pk is 1 by 8 for k equal to 0 to 7, right? K equal to 0 to 7. If I say these levels are equiprobable, probability of occurrence of any level is 1 by 8 here, right? So therefore we can say entropy of the source emitting equiprobable symbols, equiprobable 8 symbols, summation k equal to 0 to 7 pk log 1 upon pk to the base 2 equal to summation k equal to 0 to 7 1 by 8 log 8 to the base 2, 1 by 8 log 1 upon 1 by 8 is log 8, right? So now log 8 to the base 2 and 1 by 8 are constant. I can bring them out of the summation. Inside summation I have 0 to 7 summation only. it will be 8, right? So 8 getting cancelled with 8 in the denominator, I have log a to the base 2. I get 3 bits of information per symbol. I can say now for this, the person who was telling me whether is it feasible to talk in terms of real fractions or real numbers, we can say this whole integer here 3 bits per symbol, right? 3 bits per symbol. Now what it says, each level can be represented by how many bits, Yuvraj? Each level can be
Three
represented
bits.
by 3 bits, right? So what this entropy says now, it is telling us this is how you can code, right? This is how you can code. You can encode each level with 3 bits here, or you can encode on an average 3 bits per symbol, or in the previous case of 3 symbols of example I have taken now, entropy says on an average you can take 3 by 2 bits per symbol in the previous example, right? That's why I have taken this example to let you know h of s, right? If the symbols are equiprobable, right, entropy I'll get is 3 bits. This is the maximum value of the entropy of this particular source. And what this says, I can encode source symbols, right, with 3 bits per symbol on an average. Okay, I can encode each bit with each symbol with 3 bits, or on an average I can encode 3 bits per symbol. Okay, any doubts? Now what this has guided us, h of s, this has guided us how to encode. Okay, this has informed us now that how to encode, right? When I say 8 level, how many bits you need to encode? 3 bits, right, per level, right. So we are coming to know from h of s, entropy, right? Entropy is telling us how many bits per symbol you can uh, use to encode, right. So I'll just stop here and continue in the next class, right? If you have any difficulty, please let me know. If you have any doubts, any doubts?
No, sir.
No, sir.
I'm stopping the recording. As far as portion for your quiz, which is due on Tuesday, is concerned, whatever I have covered till today, today's portion will be included, right? From where I started, right? I started from waveform coding technique, right? I started from waveform coding technique, and I have come to information theory, that to entropy of a source today. Okay, right, which includes portions covered by RMD sir as well. Okay, there will be 10 questions, each question carrying 0.5 mark. Okay, so total of 5 marks test quiz, 10 questions will be set, each question carrying 0.5 marks. Any doubts? I have already uploaded material on information theory. Can you just find Swapnil Tiwari?
Yes, sir.
Just can you check whether you will be able to access the material on information theory and coding uploaded
Yes.
by me in my folder?
Yes, sir. Just one minute. No, sir. It's not there.
It's not there. Just check Yuvraj.
It is not there, sir. It's not visible in your folder and files.
ITC_PMP.pdf.
It is shown, sir. It
Yes,
is there.
sir, it is visible.
Then what's that? ITC_PM. Just open it and see.
Yes, sir, it's there.
It is
Sir,
there.
it
No?
Yes,
is
sir, your
are
notes are
able
there.
you are able to read. You are able to access it, right?
Yes, sir.
Fine. So I will stop here and we'll continue in the next class. I would like to ask you one question regarding microprocessor, certainly not with the subject digital communication. Microprocessor, this microcontroller lab, I'm talking on that. How many of you are able to use laptop? Laptop, all of you have? I'm planning to give you some programs on 8051 because it's a 2 credit lab. If it is possible, I want to send you some programs on 8051 so that you can work on it and get familiar with 8051 and you can try to do some projects on it. And once you successfully complete it, I'm planning to send programs for ARM7 LPC2148, which you are studying, right?
Yes, sir.
Yeah.
Yes, sir.
Let me know whether you are comfortable with the laptops to work on Keel Microvision software, which is required for programming 8051 or LPC2148 for that matter. Okay, if you are comfortable, let me know. Otherwise, we'll see what else can be done. Because, okay. Anything? Any questions you have?
Sir, can you repeat the name of the program you're talking about?
8051 programs, 8051 assembly programs, which has to be worked
Yes,
on.
sir.
8051 and ARM7. ARM7 is your theory subject, right?
Yes, sir. My question was, what program will we have to install on our laptops to run these things?
So what's the IDE required?
Keel Microvision software.
Keel.
Yeah, Keel, K-E-I-L, Microvision software version 4. If it is not available, I will just try to find it in my lab and upload in my files. Okay, so that you can access, download and install it. Okay, try to find Keel Microvision 4. Okay.
Sir, how will we be debugging and checking the programs then?
Simulation.
Oh, okay.
Just a simulation for the time being. Okay, I will tell you the steps so I think I'll be completing your Nlog and digital communication by next week. After that, if right, I mean, we will be free only. I thought I will do some sessions on this Keel Microvision and simulation programs, so that it will be easy for you to work on programs that we are going to give you here as soon as you come. We don't have to spend time to train you in that. Okay, I will try my best to do that.
Sir, this is only for Windows, is it?
Yeah, Windows. Yeah, I don't know about Linux operating system, whether you will get a Keel or not, but for Windows only I'm familiar with that. That's why I'm telling. Maybe there is Linux version. I will try to find the Keel Microvision 4 in the lab so that I can upload it in the Teams so that you can download and install it.
Excuse me, sir.
Yeah.
After a quick search, it seems like there are two different versions of Keel for ARM and 8051.
Yeah, there are. But Keel Microvision 4, 4, I don't know whether it is available in the net or not now. Keel Microvision 4 supports both 8051 and ARM. Okay. Hello, ARM. Whereas
Yes, sir.
Keel Microvision 5 supports only 8051, I mean, microcontroller. To get a support of ARM, you need to install some ARM package for that. Okay, that is required. Otherwise, you wait for some time before installing. I'll try to find it in the lab here, and I will upload it. Okay, so that you can install and download. I mean, download and install it. Okay. Okay.
Yes, sir.
Yeah, fine. Okay, we'll meet on Tuesday then. All the best.
Thank you, sir.
Yeah,
Thank,
bye.
thank you,
sir.
sir.
Welcome.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome.
Excuse me, sir.
Yeah.
So I have one question related to the NSIMs. Do we have a definitive date when they will begin, or a definitive month in which we'll have the NSIMs?
So far, as per the circular from the office, up to 31st of October, online mode of teaching. So far, it may change
Yes,
also. So we are expecting the classes to begin from November 1st, maybe. I don't know if things going to get settled. Okay. What do you want? Online classes or come here and work? I mean, regular classes or labs?
honestly, sir, regular classes.
Yeah. Even same here. Okay. As far as ARM is concerned, your lab manual is getting ready, right? So hope before you come here, it will be ready to go for the lab. Okay.
Okay,
So,
sir. Thank you, sir.
yeah, welcome. All the best.
Excuse me, sir.
Oh,
Sir, is the format of the sessional decided already? Like, are we going to have MCQs?
He left.